Phosphorus. A look at phosphorus as it applies to plant. This is the second part. We're going to look at phosphorus uptake. Soil microbes release immobilized forms of phosphorus into the soil solution and are responsible for the immobilization of phosphorus. Soil microbes can put out different types of chelates, which are acids that will solubilize phosphorus. By the same token, they need phosphorus in order to be able to produce ATP and nucleic acids. They will pick phosphorus up and put it into their organic compounds, which basically immobilizes it. The available phosphorus in bulk soils limits plant uptake. If you don't have enough phosphorus in the soil, you need to have it added in order to be able to uptake it properly. Phosphorus moves through the soil mainly by diffusion rather than bulk flow, which means it does not go very long distances, but rather short distances, as it is mainly insoluble. The rate of diffusion of phosphorus in the soil is slow. We're looking at 10 to the minus 12 to 10 to the minus 15 meters per second. 10 to the minus 12 meters per second would be 10 to the minus 9th millimeters, or 10 to the minus 6th microns, which means it is not moving very fast. This therefore creates a zone around the root that becomes depleted of phosphorus. The root must extend out around that area in order to be able to find it. Acquisition of phosphorus is you basically have proteoid roots increasing availability of phosphorus. Basically, they put out organic compounds that pull the phosphorus in. Or you can have mycorrhizal fungi that enhance phosphorus uptake. Of the phosphorus in the soil, 20 to 80% of it is organic. The rest is mineral. Mineral can become available to the plant in the soil solution. But notice, it's not at a very high level, and that material that is there in the solution is what can be picked up. Plant root geometry and morphology are important in maximizing phosphorus uptake. You have to have a high surface to volume ratio to favor increase of phosphorus. So phosphorus has to have the soil explored by the root. The root has to have a good sized surface ratio in order to be able to bring phosphorus in. Certain species of plants form proteoid roots, which are root clusters in response to limiting soil phosphorus supply. They will put in a lot of roots in a specific area to try and get as much phosphorus out of that soil that they possibly can. This shows you a proteoid root of Lycophyllum cordatum, and you can see how it looks like a clustered sort of root. And this is so that it can pick up phosphorus out of the soil. There are microbial interactions. Symbiotic associations by mycorrhizal fungi greatly increase the absorption of phosphorus into the roots. Mycorrhizal fungi are very important in phosphorus-limited plants where you don't have a large amount of soluble phosphorus. Therefore, they are quite important in the uptake of phosphorus, especially in areas where you may have limited phosphorus in the soil. They tremendously increase the surface area because they produce little hyphae out of the roots to explore more of the soil volume. They have a large surface to volume ratio, and therefore they increase absorption. They can grow fairly quickly from the root, more quickly than the root can expand, and that increases the area to be explored. You get increased solubilization of bound forms of phosphorus. They can solubilize material by excreting organic acids that solubilizes the phosphorus. This shows you some microbial interactions. You're looking at examples of vesicular arbuscular mycorrhizal fungi. You can see the fungal hyphae in A and C coming out of the root. The hyphae are very thin filaments, and it helps bring out the material. You can see the vesicles on these in B and D. The top line A and B are corn roots, the bottom line C and D are prairie roots. These are very important in helping the plant absorb phosphorus out of the soil environment. These are ectomycorrhizae. Ectomycorrhizae are normally produced between mushrooms and gymnosperms. There are some angiosperms which also do this. Basically, they produce these larger roots, and the larger roots have very fine filaments coming off of them, and they pick up the phosphate as well. Numerous soil microorganisms, which occur in high numbers in the rhizosphere, are known to produce phosphatase. Phosphatase is an enzyme that will help solubilize phosphate. Phosphatases are phosphate esterases which can hydrolyze organic phosphates, nucleic acids, and phosphoglycerides. Acid phosphatase in soil has been shown to be stimulated by the addition of inorganic and especially organic phosphates. They are quite important here. Another influence microorganisms can have on phosphate availability is the release of acids and chelating agents which can act upon insoluble or adsorbed soil phosphates. So microorganisms are quite important here. The uptake of phosphorus poses a problem for plants since the concentration of the mineral in the soil solution is low, but the plant requirement is high. Remember, there may be plenty of phosphorus in the soil, it just may not be in the form that plants can readily absorb. The form of phosphorus that is most readily absorbed by plants is inorganic phosphate, the concentration of which rarely exceeds 10 micromolar in the soil solution. Form in which inorganic phosphorus exists in the soil solution changes according to pH. Below pH 6, most inorganic phosphorus will be present as the monovalent phosphoric acid, H2PO4 -1, H3PO4, and HPO4 -2 will be present only in minor proportions. Uptake rates are highest between pH 5 and 6, where H2PO4 dominates, which suggests the phosphorus is taken up in the monovalent form. Plants have specialized transporters in the root-soil interface for extraction of inorganic phosphorus from solutions of micromolar concentrations. Metabolic inhibitors have been shown to rapidly reduce inorganic phosphorus uptake, indicating that uptake is energy dependent. So this is one of those materials that actually requires energy to be able to get to move it across. And this would make sense because when the material is picked up by the plant, it's going to be converted into a form that is useful to the plant, such as ATP. The transporter mechanism is most likely a co-transport with a cation of hydrogen. So you move the hydrogen across the membrane as you pick up the phosphorus. This would allow for acidification of the outside part. This would also allow for the material to generate an electrochemical gradient across the membrane, which will allow for pickup.